Hello everyone and welcome back to Tesla Harmonics. Today I want to talk about load calculations for branch and feeder circuits. Calculations to determine the electrical load for branch and feeder circuits are a necessary part of every electrical system design process. The information is used to determine the size of conductors and branch circuit overcurrent protection devices needed in accordance with NEC requirements. Properly sized conductors and protection devices ensure a safe and reliable electrical system. This module explains how branch and feeder circuit load calculations typical of residential and commercial applications are done, and it gives a lot of opportunities for extensive practice. So with that, we want to continue looking at module 26301-23, Load Calculations and Branch Circuit Feeders in the NCCER 11th edition. This will be section 1.00, Branch Circuit Loads. Okay everyone, example 1. A store has fluorescent lighting fixtures consisting of 9 fluorescent ballasts rated at 1.5 amps at 120 volts. The fixtures will operate continuously during normal business hours from 9 a.m. until 9 p.m. daily. What is the minimum circuit breaker rating required for the branch circuit that will serve this load? We will determine the branch circuit load, then calculate 125% of the load because it's continuous, and determine the minimum size circuit breaker required. Determine the branch circuit load. 9 times 1.5 amps equals 13.5 amps. Calculate 125% of the load. 13.5 amps times 1.25 equals 16.88 amps. Determine the minimum size circuit breaker required. It would be a 20 amp, since the next highest value greater than 16.88. Example 2, what is the maximum continuous load that may be connected to a 30 amp, 120 volt fuse divided by 125%? 30 amps divided by 1.25 equals 24 amps. Example 3, how many receptacle outlet devices in a non-residential building can be connected to a 20 amp, 2-wire 120 volt circuit? Assume that the receptacles serve non-continuous loads. Determine the branch circuit capacity. Divide available load by the value of each individual outlet load and round down. Determine the branch circuit capacity would be 20 amps times 120 volt equals 2400 VA. Divide available load by the value of each individual outlet load. 2400 VA divided by 180 VA equals 13.33. Round down and it would be 13 receptacle outlets. Example 4. An office manager has purchased a new state-of-the-art copy machine. The nameplate rating of the copy machine is 17 amps at 120 volts. What is the minimum branch circuit rating required to serve this equipment? Determine the current carrying capacity of a 20 amp circuit to see if it can manage the 17 amp load. 20 amps divided by 1.25 equals 16 amps. Determine the current carrying capacity of a 30 amp circuit to see if it can manage the load. 30 amps divided by 1.25 equals 24 amps. Example 5. What is the maximum lighting load that may be connected to a 20 amp branch circuit supplying a piece of fixed equipment that has a rating of 8.5 amps at 120 volts? The equipment rating is less than 50% of the rating of the 20 amp branch circuit, therefore 11.5 amps of non-continuous lighting may be added. A commercial dishwasher has a nameplate rating of 14.7 amps, 208 volts, 3-phase. During busy times in the restaurant, it is anticipated that the dishwasher will be turned on and operated for more than 3 hours at a time, making it a continuous load. What is the minimum branch circuit rating required to power the dishwasher? We're going to multiply by 125% and determine the minimum branch circuit rating. Multiply by 125%. 14.7 amps times 1.25 equals 18.38 amps. Determine minimum branch circuit rating. 20 amps, since this is the next highest value greater than 18.38 amps. It is determined that by combining branch circuits on a project, 2 costly runs of conduit can be eliminated. The branch circuits are to be pulled in a single conduit. All the conductors in the conduit will be current carrying conductors of the same size and insulation type. What is the D-rated ampacity of each 8 number 12 THHN copper conductors when pulled in a single conduit? We're going to use NEC table 310.16 to determine the ampacity of number 12 THHN. We're going to use NEC section 310.15C1 to determine D rating, and we're going to calculate the new ampacity. Use NEC 310.16 to determine the ampacity of number 12 THHN, which is 30 amps. Use NEC 310.15C1 to determine D rating, 70% of the value. Calculate the new ampacity. 30 amps times 0.7 equals 21 amps. Example 2. What is the maximum load that may be connected on each of 6 number 2 THWN copper conductors in a single conduit? We will use NEC table 310.16 to determine the ampacity of number 2 THWN. We will use NEC section 310.15C1 to determine D rating, and then we will calculate the new ampacity. Use NEC table 310.16 to determine the ampacity of number 2 THWN, which is 115 amps. Use NEC section 310.15C1 to determine D rating, which will be 80% of the value. Calculate the new ampacity. 115 amps times 0.8 equals 92 amps. Example 3. A branch circuit is required to supply a non-continuous load with a nameplate rating of 55 amps. The equipment is in a plant located in a room with plastic extrusion equipment that gets very warm. The ambient temperature in the room is 92 degrees Fahrenheit, 33.3 degrees Celsius. What is the minimum size of THHN copper conductors allowed to supply the new load? We will use NEC table 310.16 to determine a conductor with appropriate ampacity rating. We will use NEC table 310.15B11 to determine correction factor. And then we will calculate to see if the selected conductor meets the requirement. Use NEC table 310.16 to determine a conductor with appropriate ampacity rating. Try number 8 THHN with 55 amp ampacity rating. Use NEC table 310.15B11 to determine correction factor. 0.96 would be the correction factor. Calculate to see if selected conductor meets the requirement. 55 amps times 0.96 equals 52.8 amps. Number 8 THHN does not meet the requirement. Try again with number 6 THHN. Example 4. A branch circuit conductor with a power of 16 amps of continuous loads. The conductors to be used are THHN copper. They will be installed in a raceway with a total of 12 current carrying conductors and routed through an area with an ambient temperature of 105 degrees Fahrenheit or 40.5 degrees Celsius. What is the minimum wire size and overcurrent protection device required for the circuit? We'll multiply by 125%. We'll use NEC section 310.15C1 to determine adjustment factor. We'll use NEC 310.15B11 to determine temperature derating. We'll use NEC table 310.16 to determine the correct wire size. Multiply by 125%. 16 amps times 1.25 equals 20 amps. NEC section 310.15C1 to determine adjustment factor. 20 amps divided by 0.50 equals 40 amps. Use NEC section 310.15B11 to determine temperature derating. 40 amps divided by 0.87 equals 45.98 amps. Use NEC table 310.16 to determine the correct wire size, which will be number 8 THHN. Voltage drop derating for single-phase circuits. Formula 1 is voltage drop equals 2 times L times R times I divided by 1,000, where VD equals voltage drop, L equals load center or total length in feet, R equals conductor resistance per 1,000 foot, and I equals current. Formula 2, voltage drop equals 2 times L times K times I divided by C mil, where VD equals voltage drop, L equals load center or total length in feet, K equals constant of 12.9 for copper conductors or 21.2 for aluminum conductors, I equals current, and C mil equals conductor cross-sectional area in circular mils. Example 1. The length of a 120 volt 2-wire branch circuit is 95 feet. The non-continuous load is 14.5 amps. If number 12 THHN solid copper conductors are used, will the voltage drop for the branch circuit exceed 3%? Use the first voltage drop formula in NEC Chapter 9, Table 8 to determine the resistance. Use the first voltage drop formula in NEC Chapter 9, Table 8 to determine the resistance. Voltage drop equals 2 times 95 feet times 1.93 ohms times 14.5 amps divided by 1,000 feet. Voltage drop equals 5,317.15 divided by 1,000 equals 5.31715 volts, rounded to 5.32 volts. 5.32 volts divided by 120 equals 0.0443. 0.0443 times 100 equals 4.43%, which would exceed the 3% voltage drop. Which size THHN solid conductor branch circuit conductors would be recommended for a single-phase non-continuous branch circuit load of 23 amps at 240 feet? The length of the circuit is 130 foot. We will use the second voltage drop formula in NEC Chapter 9, Table 8 to find the circular mille value. We would use the second formula in NEC Chapter 9, Table 8 to find circular mille value. Voltage drop would equal 2 times 130 times 12.9 times 23 divided by 10,380 circular milles. Voltage drop would equal 77,142 divided by 10,380 would equal 7.4317 volts, rounded to 7.43 volts. 7.43 volts divided by 240 equals 0.031 volts. 0.031 times 100 equals 3.10%. Number 10 THHN does not meet the requirement. We would try again with number 8 THHN. Example 3. A 240 volt single phase 3-wire branch circuit has multiple power outlets consisting of 3 fixed 240 volt loads. The 3 loads are 30 amps at a length of 60 foot, 30 amps at 80 foot, and 20 amps at 100 foot. What size THHN copper conductors would be required? We will determine the length for the load center. We will use Table 310.16 to determine which conductor to select, and NEC Chapter 9, Table 8 to find the circular mille value. And then we will use the second formula to check the voltage drop. Determine the load center length, multiply the outlets by their distance from the circuit source, and find the sum of the 3 results. We have 60 foot at 30 amps is 1800, 80 foot at 30 amps is 2400, and 100 foot at 20 amps is 2000. Add those together and we get 6200. Divide by the sum of the 3 loads. 30 amps plus 30 amps plus 20 amps equals 80 amps. 6,000 divided by 80 amps equals 77.5 foot. Use NEC Table 310.16 to determine which conductor to select in NEC Chapter 9, Table 8 to find the circular mille value. Number 4, copper THWN or THHN conductors with a 41,740 circular mille. Use the second formula to check for voltage drop. Voltage drop equals 2 times 77.5 foot times 12.9 ohms times 80 amps divided by 41,740 circular milles, and we get 3.8322 volts, rounded to 3.83 volts. The voltage drop for balanced 3-phase circuits can be calculated by substituting the square root of 3 for the value of 2 in the previous formulas. Formula 1, voltage drop would be the square root of 3 times L times R times I divided by 1,000 foot. Formula 2 would be voltage drop equals square root times L times K times I divided by circular mille. Example 1. What is the voltage drop in a 208 volt 3-phase branch circuit with a load of 32 amps? It is 115 foot from the circuit breaker to the load, and number 8 stranded copper conductors are in place. We would use NEC Chapter 9, Table 8 to determine the resistance and the first 3-phase voltage drop formula to determine the voltage drop. Example 1. Voltage drop equals 1.732 times L times R times I divided by 1,000. Voltage drop equals 1.732 times 115 foot times 0.778 times 32 amps divided by 1,000 foot. Voltage drop equals 4,958.785 divided by 1,000 foot equals 4.9587 volts, rounded to 4.96 volts. The maximum voltage drop permitted is 208 volts times 0.03 equals 6.24, so the conductor selection is acceptable. Example 2. Which size THHN copper conductors would be recommended for a 208 volt 3-phase 4-wire feeder with a length of 150 feet from the source to a fixed continuous load of 160 amps? We will determine the minimum ampacity required and use NEC Table 310.16 to select the conductors, and we use the second 3-phase voltage drop formula to check if the selected conductors are satisfactory. The minimum ampacity required would be 160 amps times 1.25 for the continuous load equals 200 amps. That would be a 3-aught THHN copper conductor. We will check if they are satisfactory. Voltage drop equals 1.732 times 150 foot times 12.9 ohms times 160 amps divided by 167,800 circular mils would equal 3.1956 volts rounded to 3.2 volts. The maximum recommended voltage drop is 208 volts times 0.03 equals 6.24, so the conductor selection is acceptable. Branch circuit ampacity. What is the ampacity of a single-phase load with a nameplate rating of 5.5 kW at 240 volts? We would divide the volt amps by the circuit voltage. Find the volt amps and then divide the circuit voltage. 5.5 kW times 1000 equals 5,500 VA. 5,500 VA divided by 240 volts equals 22.92 amps. Example 2. What is the ampacity of a 3-phase electric water heater with a nameplate rating of 20 kW at 208 volts? We will divide the volt amps by the voltage multiplied by the square root of 3. 20 kW times 1000 equals 20,000 VA. 20,000 VA divided by 208 volts times 1.732 would equal 55.52 amps. Here's some trade terms you should read over and become familiar with for this section. And some review questions for this section. What is the maximum continuous load that may be connected to a 20 amp, 120 volt fuse? Is it 10 amps, 16 amps, 20 amps, or 25 amps? That's going to be 16 amps. The voltage drop for a single phase 208 volt circuit with a load of 28 amps served by a number 8 stranded copper conductors at a circuit length of 160 feet is 5.87 volts, 5.98 volts, 6.78 volts, or 6.97 volts. And that's going to be 6.97 volts. The ampacity of a single phase 120 volt load rated at 800 VA is 2.87 amps, 4.38 amps, 5.78 amps, or 6.67 amps. And that's going to be D, 6.67 amps. Alright everyone, that was it for that section. Next section will be 2.00 residential branch circuit requirements, and I will see you over there.